Hello, my name is Akshar Chavan. I will be talking on our project towards high quality battery life for autonomous mobile robot fleets. Autonomous mobile robots are the robots that navigate in a working environment performing objective tasks by the use of sophisticated sensors, artificial intelligence and machine learning approach. They they are widely used for security applications, hospitals and healthcares, hospitality, last mile delivery and warehouses. They consist of computing boards to perform the computation task, locomotion components to make them mobile, sensors to do objective task or locomotion tasks, and energy sources such as battery, which provides energy to the other components to do their work. This image is of our autonomous mobile robot in our lab, which is equipped with all these components. In this project, we want to achieve several objective tasks, including task allocation over a long period of time. Here we see in this example case where AMR1 is performing navigation task 1 and the objective task associated to the navigation task 1, which may include face recognition, inventory checks, finding holes in the fence. Okay. As AMRs generally uses battery as an energy source, they need to recharge batteries to continue performing the task. Therefore, we need to schedule charging of an AMR. Usually the charging stations are limited. As we can see in this example, we have only one charging station and 3 AMRs. Therefore, we need to coordinate the task allocation and charging schedule for minimizing the task downtime. We also want to have a sustainable solution as battery life is affected by how the battery is utilized. As we can see in the figure, utilizing the battery between 80% and 20% of the total battery capacity results in the battery reaching the 80% of the capacity retention within less than 4,000 dynamic stress test cycles. Then comparing the battery when it is utilized from 100% to 50% of the total battery capacity. Okay. So therefore, using the battery within the SOC threshold ensures desired battery life. We assume that these thresholds are provided by the system manager. In this figure, we see that the AMRs are operating within the minimum and maximum thresholds by frequently, yes, but they are being frequently scheduled to recharge. By frequently scheduling to recharge, they utilizes more energy to travel to and from the charging station. We consider this energy as wasted energy, as it is not utilized to perform objective tasks. Energy utilized to perform objective tasks is considered as useful energy. We can ensure high quality battery life by minimizing the number of recharges that can be achieved by starting and stopping the recharge closer to the SOC thresholds, ensuring both desired lifespan and low energy wasted to go to the charging station and come back. Therefore, we have a new objective to coordinate the task allocation and charging schedule for high quality battery life. Several research studies on AMR task allocation provide multiple robot task allocation or energy efficient path planning or energy aware task allocation of multiple AMRs, but they do it either by focusing only on locomotion energy or do not coordinate the charging decisions. Several other research studies provide charging solutions for a single AMR or multiple AMR with limited charging stations, but do not perform joint task allocation. Our solution provides joint task allocation and charging schedule decisions for multiple AMRs with limited charging station, minimizing the task downtime and ensuring high quality battery life. So, statistically allocating tasks only at the beginning of the working period may lead to poor performance due to energy modeling errors. Therefore, we make our task and charging decisions robust to the modeling errors. Decisions made in the current period affect the decision results for the future period. Therefore, we plan for the current period by estimating the decisions for the future period. Therefore, we do multi-period planning. The complexity of the multi-period planning increases with the increasing number of AMRs, charging station, task, and decision periods. Therefore, we divide the multi-period planning in different stages. Our objective is to minimize the task downtime and battery life quality degradation as shown in the total objective cost equation. In this equation, the function in this objective function, we provide the weight Q that can be used by the system manager to trade off between the task downtime and the degradation cost of the battery. In the upcoming slides, we will show the effect of this wait function on the task downtime and the life quality degradation of the battery. The figure here shows the block diagram for our approach, which is explained in detail in the next slides. At the beginning of every decision period, the TCM framework first reads the available energy of the AMRs, then update the state variables and schedules the charging of all the AMRs in stage 1. Then in stage 2, it selects the task to allocate and assigns the AMR task to the AMR until no task can be allocated to the AMR. It then gets the task and it then communicates the task and charging decisions for the current period to the respective AMRs. To explain the two stages, we use an example solved by the TCM with 3 AMRs, 2 navigation tasks, 5 objective tasks, 1 charging station, and 24 decision periods. We use energy level, availability of the AMRs, task and charging decisions made in the previous period as state variables. Consider an example as shown in this figure here. The solid line indicates the actual SOC of the AMRs and the dashed line indicates the estimated SOC of the AMR through multi-period planning. In period 4, we see that the actual SOC of the AMR is lower than the estimated SOC. Okay. This is because of the energy modeling errors. To handle this energy modeling error, we use updated energy level to get the charging and task allocation decisions. We also consider minimizing the changes from the previously estimated solution and the current updated solution. In this slide, we explain the stage 1 of our proposed approach, which is to get the charging schedule of the AMRs. It starts by selecting AMR that is waiting the longest to complete the recharge, and then do a case-based objective cost comparison where case 1 is to continue charging or start charging in the current period, and case 2 is to stop charging or do not recharge in the current period. It then finds out the estimated total objective cost and compare them. If it is convenient to continue recharge or start recharge in the current period, then it schedules to recharge. If it is not convenient to do so, then it will not schedule the AMR to recharge in the current period. The charge cost comparator is based on the current state of charge of an AMR, availability of the charging stations, and availability of the other AMRs for task execution. It provides an output or an estimated charging schedule of an AMR and the availability period of an AMR to perform the tasks in the future periods. The task scheduler algorithm uses the estimated availability of the AMR in the future period to schedule the task. We make the decisions of the task allocation based on the AMR similar allocation cost comparison, which tries to maximize the total number of tasks allocated to the AMR by progressively comparing the total objective cost of allocating n tasks against allocating n-1 tasks. If allocating n-1 task is more convenient, then it continues comparing the n-1 task against n-2 task. This comparison continues until two cases are occurred. First, the cost of allocating higher number of tasks is more convenient than the cost of allocating a lower number of tasks. In this case, those tasks are then allocated to the AMR. Second, the cost of allocating no task is lower than cost of allocating at least one task. In that case, the AMR is then made available to recharge. Here we explain the stage 2 of our proposed algorithm, which is to get the task allocation decision for all the AMRs, which is done in 2 steps. First AMR selection and then task allocation. In AMR selection, we first select the navigation task with the highest total objective cost contribution, and then temporarily allocate objective task associated to that navigation task using the allocation cost comparator explained in the previous slide to the available robots. This results in getting an estimated SOC of the available robots. Then we get the waiting time based on the availability of the charging stations and select the AMR with the lowest energy level and the waiting time. We select the AMR here with the lowest energy level because the AMR with the higher energy level will be able to take over the remaining task of the AMR with the lower energy level. In this case, AMR2 has the lowest energy and it is scheduled to recharge in period 3 where the charging station is available. Therefore, it has no waiting time. And the AMR selection selects the AMR2 and finalizes the temporarily allocated task on AMR2. Then in the next iteration of AMR selection, it selects navigation tasks 2, which had the second highest total objective cost contribution, and then allocates the temporary objective task associated to that navigation task to the available robots, which is AMR1 and AMR3. Here, if we select AMR1, then AMR1 has to wait for 2 periods, that is in period 5 and period 6, because of unavailability of the charging station, which will increase the wait time and which may result into increase in the downtime. And therefore, the AMR selector selects AMR3 and finalizes the temporarily allocated task on AMR3. This process continues until all the AMRs have their task scheduled for the future periods. Here we see that in period 2, AMR1 was able to take over the remaining of the objective tasks left, which were left by the AMR2 in the period 2. Okay. We perform our experiments on model parameters collected from Hydra 1, a prototype AMR, and did 600 simulation experiments with different parameters range as shown in this table. We use 3 performance metrics in our paper. First is the task allocation, which is the percentage of the objective task allocated across the navigation task. The second is energy usage effectiveness, which is the ratio of the total energy utilized over the useful energy. Energy usage effectiveness of 1 is best, which means that 100% of the energy utilized is used to do useful work, that is the performing objective tasks. Energy usage effectiveness also depends upon the distance from the charging station. If the distance from the charging station of the navigation task is higher, then the energy usage effectiveness is higher, as we can see in this figure. The third performance metric is the state of charge violation, which is the cumulative percentage of the violation of the SOC thresholds. We have 3 baselines. First is minimum min dt, which focuses mainly on minimizing the task downtime, therefore utilizes the total battery capacity and do not operate within the SOC thresholds, and therefore do not consider the battery life degradation as shown here in the figure. Mean DTC, which is similar to mean DT, but it ensures battery life degradation and operates within the SOC threshold. Then the third is the MINLP, which is our proposed program formulation solved in Groby optimization solver. This slide shows the average result of 600 experiments compared to the proposed approach, TCM, with the baselines on the performance metrics explained in the previous slide. We see that the task allocation of mean DT is highest among all the baselines and TCM, because it utilizes the total battery capacity and do not take into account the battery life degradation. Therefore, it has the highest SOC violation. Mean DT also has an energy usage effectiveness of 1.34, that is 75% of the total energy is utilized to perform objective task. Mean DTC, MINLP, and TCM have a similar task allocation percentage, as they operate within the minimum and maximum threshold. Therefore, they have almost negligible SOC violation compared to mean DT. TCM has the best energy usage effectiveness of 1.25, which is 80% of the total energy utilized to performing objective tasks. As seen in the previous slide, MINLP and TCM both provide similar performance matrices in all matrices. However, the main problem of MINLP is that it takes exponentially increasing time to find a solution for higher problem complexity. TCM achieves a performance ratio of 1.15 in a fraction of execution time, as we can see in average run times versus problem instance complexity figure. As explained in one of the previous slides, the total objective cost contains a weight value, which allows the system manager to decide how much weight to be given to the task allocation objective versus battery life quality objective. As you can see, increasing the weight value forces the TCM to give more importance to preserve the life quality of the battery at the cost of task allocation performance. We saw that the desired lifespan is not sufficient to ensure high quality battery life. Therefore, we need to coordinate the task allocation and charging decision to ensure the battery life. Through the experiment results, we saw TCM provides high quality battery life with a performance ratio of 1.15 compared to MINLP. TCM also provides the flexibility to the system manager to trade off between the task downtime and battery lifespan quality. Thank you.